Zero Trust, an architect's view, control plane versus data plane. Welcome back to the Tuff Networks channel. If you walk onto the expo floor of any major cybersecurity conference today, you will be screamed at by 1,000 banners, all saying the exact same thing. Buy our Zero Trust. They will try to sell you a VPN replacement. They will try to sell you an identity provider. They will try to sell you a firewall with a fancy new sticker on it. But here is the hard truth that most vendors don't want you to focus on. You cannot buy Zero Trust. Zero Trust is not a product. It is not a SKU. It is not a piece of software you install on a server. Zero Trust is a philosophy. It is an architectural paradigm shift. And if you are an engineer or an architect, you need to stop thinking about it as a tool and start thinking about it as a fundamental decoupling of the control plane from the data plane. Welcome back. Today we are going to tear down the marketing buzzwords and rebuild Zero Trust from the ground up, looking at it strictly through the lens of systems architecture. We are going to explore why the castle and moat is dead, how identity-based micro-segmentation actually works under the hood, and most importantly, we are going to deep dive into the separation of decision-making and traffic forwarding. Let's get into the architecture.
Part 1. The failure of implicit trust. To understand the architecture of Zero Trust, we first have to speak the language of the architecture we are replacing, the perimeter model, or the castle and moat. For 40 years, enterprise networking was built on a simple, geographic lie. We assumed that location equaled trust. If you were sitting at a desk in the headquarters, plugged into an Ethernet jack, you were trusted. If you VPN'd into the network, you were virtually placed inside the building, and therefore, you were trusted. From a network engineering standpoint, this relied on implicit trust. Once a packet cleared the firewall, the moat, it was free to move laterally. It could ping the domain controller. It could scan for file shares. It could attempt to SSH into databases. The internal network was a flat, open field. This architecture fails today for two reasons. 1. The perimeter has dissolved. Users are everywhere. Data is in the cloud, and devices are rarely on-prem. 2. And more critically, identity has nothing to do with IP addresses. The fundamental thesis of Zero Trust is simple. Never trust, always verify. But that's just a slogan. As architects, how do we translate that into a diagram? We do it by removing network locality as a factor for access. We stop caring where the user is, and we stop caring about the network segment they are physically connected to. Instead, we move the perimeter from the edge of the network to the edge of the user. The identity becomes the new perimeter. The core mechanism, control plane versus data plane. This is the most important part of this entire discussion. If you take nothing else away from this video, understand this distinction. In a traditional network, the device that routes the traffic is often the same device making the security decision, usually based on simple 5-tuple rules: source IP, destination IP, source port, destination port protocol. In a Zero Trust architecture, specifically following the NIST 800-207 standard, we completely decouple the control plane from the data plane. Let's define them. The control plane is the brain. In formal terms, this is the policy decision point, or PDP. This is where the logic lives. It is an engine that ingests signals. It looks at the user's identity, the device's health, the geolocation, the time of day, and the sensitivity of the application being accessed. It takes all these inputs and calculates a risk score. It decides, should this entity talk to that resource? The data plane is the muscle. This is the policy enforcement point, or PEP. This is the actual gateway, proxy, or agent that sits in front of the application or resource. Its job is boring. It doesn't think. It simply blocks all traffic by default. It only allows packets to pass if, and only if, the control plane explicitly tells it to. Here is the architectural flow of a Zero Trust connection. Imagine a user, Alice, wants to access a legacy billing application hosted on a server in AWS. In the old world, Alice connects to a VPN. She is now on the network. She has an IP address. She routes directly to the server. In a Zero Trust world, here is the sequence. 1. The request. Alice's laptop sends a request not to the application, but to the control plane, the broker. 2. The interrogation. The control plane pauses everything. It doesn't let a single packet reach the billing app. It turns to the identity provider and asks, is this Alice? It turns to the endpoint detection and response, EDR system, and asks, is this laptop infected? Is the OS patched? Is the disk encrypted? 3. The decision, the control plane, aggregates these signals. If Alice is who she says she is, But her laptop has malware? The control plane says no, access denied. The data plane remains closed. 4. The tunnel. If everything looks good, the control plane instructs the data plane, the gateway sitting in front of the app, to accept a connection from Alice. 5. Ephemeral connectivity. This is key. A micro-tunnel is spun up specifically for Alice, specifically for that one application on that one port. It is an ephemeral one-to-one connection. Alice cannot see the server next to the billing app. She cannot port scan the subnet. She has a quote segment of one. This separation is powerful because the data plane, the application side, essentially goes dark to the public internet. You don't need open inbound ports on your firewall anymore. The gateway reaches out to the control plane to check for pending connections. If you scan the public IP of a zero-trust gateway, it shouldn't respond. It's a black hole. This is often called dark cloud architecture. Part 3. Identity-Based Micro-segmentation. Now that we understand the mechanism, let's talk about the result, micro-segmentation. In the past, segmentation was a nightmare. It meant VLANs. It meant access control lists, ACLs, on switches. It meant managing thousands of firewall rules that no one wanted to touch for fear of breaking a production app. It was network-based segmentation. Zero Trust enables identity-based micro-segmentation. Because the control plane is making decisions based on who you are, not where you are, we can create incredibly granular policies without touching a single router config. We can say, the engineering group can access the source code repository, but only from corporate managed devices, and only if they have MFA enabled. If an engineer unplugs their laptop and walks to the marketing department, their access doesn't change. If they fly to a coffee shop in Tokyo, their access doesn't change. The policy follows the identity. This solves the lateral movement problem. Let's look at a cyber attack scenario. A hacker compromises a user's laptop via a phishing email. In a VPN environment, the hacker now has a foothold on your network. They run a tool like Nmap or Bloodhound. They map out the network. They find a vulnerable server, jump to it, dump credentials, and elevate privileges. They move laterally until they find the crown jewels. In a zero-trust architecture, that compromised laptop is in a straitjacket. Even if the hacker has the user's password, the control plane might see that the request is coming from an impossible travel location, or that the device health status has changed because the hacker disabled the antivirus. The control plane cuts off access immediately. But even if they do get past the authentication, they can only see the specific applications the user is authorized for. They cannot see the domain controller. They cannot see the file shares. The blast radius of the breach is contained to a single user and a single session. Part 4. The continuous trust evaluation. Another major architectural difference is the concept of continuous verification. In the old world, authentication was a gate. You put in your password, the gate opened, and you were in until you logged out. We call this session-based trust. Zero Trust requires continuous evaluation. Just because you were trusted at 9 a.m. doesn't mean you are trusted at 9:05 a.m. The control plane is constantly listening to the signal telemetry. Let's say Alice is logged in and working. Suddenly, her EDR agent detects a ransomware signature on her machine. The EDR agent sends a signal to the control plane. In real time, the control plane revokes the token. The data plane immediately severs the connection. The session is killed midstream. This dynamic response capability is impossible with standard firewalls and VPNs. It requires that tight integration between the identity provider, the device management, and the network enforcement point. Part 5. Comparison, performance, and architecture types. Now let's talk about how this looks physically, because there are performance implications here. There are generally two ways to deploy this architecture: agent-based and agentless. Agentless is usually for unmanaged devices or third-party contractors. It typically looks like a reverse proxy. The user goes to a web portal, authenticates, and the portal renders the application in the browser. It's great for web apps, but terrible for thick clients or legacy protocols. Agent-based is the gold standard for employees. A lightweight piece of software sits on the endpoint. This agent acts as the local forwarder. It intercepts the traffic on the loopback interface and tunnels it to the Zero Trust gateway. From a performance standpoint, this is vastly superior to the traditional hub-and-spoke VPN model. Think about the old way. You have a user in London. The VPN concentrator is in New York. The application is a SaaS tool hosted in London. The user connects to the VPN. Their traffic goes from London, across the Atlantic to New York, gets hairpinned, goes back across the Atlantic to the SaaS app in London, and then returns. It's a latency nightmare. Zero Trust architecture utilizes a distributed edge. The control plane is cloud-native and distributed globally. The data plane, the enforcement nodes, are also distributed globally. The user in London connects to the nearest point of presence, POP, in London. The policy is checked there. If they are accessing the internet or a SaaS app, they break out directly to the internet from London. This is direct-to-internet breakout. We are no longer backhauling traffic to a central data center just to pass it through a security stack. We are pushing the security stack to the edge, as close to the user as possible. This improves latency and user experience, which is rare in security. Usually, more security means a worse user experience. Zero Trust, done right, actually makes the network faster. Part 6. Real-world scenarios and implementation. Let's walk through a concrete scenario to solidify this. Scenario: the DevOps engineer and the SSH key. You have a developer who needs to SSH into a production Linux server to debug an issue. The old way: the developer connects to the VPN. They open their terminal. They type SSH user at 10.0.1.50. They use a static SSH key stored on their laptop. Asterisk risk: if the laptop is stolen, the key is stolen. If the VPN is compromised, the server is exposed. The developer also has network access to every other server on that subnet. The Zero Trust way: 1. The developer opens their terminal and types the SSH command. 2. The local ZT agent intercepts the traffic. 3. It prompts the developer for MFA, perhaps a biometric touch on the laptop. 4. The request goes to the control plane. 5. The control plane verifies the user and device health. 6. The control plane authorizes the session. 7. Here is the magic. The system can inject a short-lived ephemeral SSH certificate into the session. The developer doesn't even have a static key on their machine. 8. The data plane connects the developer to the server. 9. The developer does their work. 10. When they log out, the certificate expires. The tunnel collapses. There are no open SSH ports to the internet. No static keys to lose. No lateral movement possibilities. Scenario: the third-party contractor. You hire a marketing agency. They need access to your internal Jira instance, but nothing else. The old way: you ship them a corporate laptop, expensive, or you give them a VPN account and try to restrict it with complex firewall rules, difficult and prone to error. The Zero Trust way: you use clientless browser isolation. The contractor uses their own iPad or laptop. They navigate to a URL. They log in with their own credentials, federated identity. The Zero Trust gateway renders the Jira page as a pixel stream to their browser. Asterisk data never touches their device. They cannot copy/paste. They cannot download files. They cannot see the network. They see pixels.
The challenges. Why isn't everyone doing this? If this is so great, why does the castle and moat still exist? Because getting to this architecture is hard work. 1. Legacy debt. You cannot just turn on Zero Trust for a mainframe application built in 1990 that uses hard-coded IP addresses. You often need app connectors, or sidecar proxies, to translate modern identity protocols into something the legacy app understands. 2. Knowing your traffic. You cannot build a policy if you don't know how your applications talk to each other. To implement micro-segmentation, you first need a discovery phase to map out application dependencies. If you block traffic without knowing it's required, you break production. 3. The Zero Trust washing of the market. As I mentioned at the start, vendors are confusing the issue. They sell you a ZTNA, Zero Trust Network Access tool, but if you don't integrate it with a strong identity provider and a strong endpoint protection platform, you haven't built Zero Trust. You've just bought a fancy VPN. The architect's checklist. So, to summarize, Zero Trust is not a product. It is an architecture defined by 1. Decoupling. Separation of the control plane, decision, and data plane, enforcement. 2. Identity centricity, policy, is based on user plus device plus context, not IP address. 3. Micro-segmentation, reducing the blast radius to a segment of 1. 4. Continuous verification. Trust is ephemeral and constantly reevaluated. As an architect, your job is to design systems where the network is assumed to be hostile. You assume the attacker is already inside, and you build your controls around the data and the user, ensuring that every single packet is authorized before it is allowed to flow. Don't buy the hype. Build the architecture. Thanks for watching. If you want to see a deep dive into how we configure the specific policy engines for this, or how to handle break and inspect for encrypted traffic within a zero trust model, let me know in the comments below. See you in the next one.